Hey guys, so let's get started on part two of chapter 7. This is kind of a kind of random miscellaneous like stuff left out of the previous section of the chapter. So you'll see that it might seem a little bit disjointed. The first thing that this chapter talks about, or this part of the chapter talks about, is radicals. And radicals are where you have an odd number of electrons in total. And so instead of pairing them up as we've been doing so far, you'll have at the end one leftover electron where it will go to the most central atom. So in these cases, there's always going to be an unfilled octet for one of the atoms. And oftentimes, because you fill out the terminal atoms first, the atom that gets the unpaired electron usually becomes the middle atom. And so here we have an example of NO2. And so each oxygen gives you 6, so that's 12 in total, and the nitrogen gives you 5, so that's a total of 17 electrons, valence electrons. And if we go through the motion, I'm going to do it over here on the side. We have NO2, and over here, so out of the 17, I've already used up two of my bonds, so I have 4 electrons in there. 1, 2, 3, 4 of them. So minus 4. I'm left with 13. Then I want to give each electron, or each atom, oxygen atom, or all the terminal atoms, enough electrons to fill out their valence shell. So I just gave them 12. And now I'm left with 1. And in that case, my 2 terminal atoms will have already been filled, and I could give 1 electron to my nitrogen here, and that's in the middle. So this 1 nitrogen, notice how it's unpaired. These are paired, these are paired, and these are paired. And so we call this a radical. And radicals are important because they're actually quite reactive and are the primary reason why UV might cause cancer, or that it's basically a lot of problematic things happen because of radicals in our body. The main one, I guess, would be the UV damage. Here's one thing I'm missing over here. So as you can see, my nitrogen here can still make one more double bond, right? So what I'm going to get is these 2 pairs, or any pair of electrons, will form a bond. Now I'm going to tell you why I did that. It has nothing to do with radicals, but I wanted to mention it. Too many electrons here. And so the reason I did that is because nitrogen now has 7 electrons. 1, 2, 3, 4, 5, 6, 7. All right, and whereas before it only had 5. So at least now with this double bond, it's closer to its octet. It's 7 out of 8 electrons filled. I can't do that again up here, because if I did that, then I would have 9 electrons, and I can't have 9 electrons. So this is where I stop here, and this is going to be the final Lewis structure for my NO2. Okay. Next is the electron dot structures of carbons and hydrogens, and in particular what we call hydrocarbons. And hydrocarbons are quite common because they make up all organic molecules. They are made up of C's and H's only. And what's important to know here is that in all cases, C's make 4 bonds and H's make 2 bonds. And I'll even take this one step further and tell you that oxygens make 2 bonds. Sorry, my mistake. Hydrogens don't make 2 bonds, they make 1 bond. Okay? And so it should be singular here. All right, so this, I would say, is something that you would need to memorize. So if I told you something like, draw me the electron structure of this, then you need to know that carbons make 4 bonds, so they'd have to be attached to each other, and that the only possible configuration for this is to have this. All right, and all we did was we followed these simple rules that carbons make 4 bonds, H's make 1 bond, and oxygens make 2 bonds. We're going to learn about that in the next chapter in more detail, but for now, this is what you need to know, is that these simple rules. And then once you know that, filling up the Lewis structure diagram is the same as what we did before. So what you would do is, you would find out the total valence electrons, and subtract the amount of bonding electrons, then give the remaining as lone pairs. Okay. And then lastly is to identify, oh, actually, no, there's two more things. First, let's talk about resonance structures. And so if I were to ask you to draw an electron structure for O3, you would understand it's 3 oxygen molecules, or atoms rather, so there's 18 valence electrons. It would look like this. You have 1, 2, 3, 4 that are being used up. So 18 minus 4 would be 14. And so then I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 electrons being used on the terminal atoms, and therefore I would have to have two electrons on the central atom. Now the central atom here is not satisfied because it only has 6 electrons. So one of these oxygens will give both of its lone pairs to form this double bond. Okay, up until now, this is all that we've noticed. We haven't talked about resonance yet. So to talk about that, what you need to understand is that whether I took these electrons and moved them to make the double bond, or I took these electrons to move them to make the double bond, it actually made no difference. Okay, because it's symmetrical and they're equally good, equally fair to get electrons from there. So when you have that option, then what you have is a resonance structure. All right, so these two, if I took the electrons from the left oxygen, I got this molecule on the left, and if I took the electrons from this oxygen, then I got this molecule on the right. But these molecules are equivalent because you end up with the same amount of stability. And so these are called resonance structures of each other. Okay. And then the last thing now, and this was a question that was asked in class when we were talking about the Lewis structures, was that how do we determine the charge of a molecule when they are drawn in a Lewis structure? Is that something that we need to do? And my answer was not at this moment, but it is yes now at this moment. So let's figure that out. So to do that, you would need to be given the Lewis structure, right, which is right there. And the question is determine the charge of each atom. And so we have to do that. And there's a rule for that. The equation to use is here. So for formal charge of each atom, all right, first of all, determine the number of valence electrons given to it when it's at the periodic table. So since in this case oxygen is in the 6th group, it has 6 valence electrons. All right, it's given 6 valence electrons right off the periodic table. Then subtract half of the bonding electrons. So this, if we're talking about this atom here, it's got 1, 2, 3, 4 bonding electrons. So subtract half of that, 1/2 of 4. Okay. And then finally, subtract all of the non-bonding electrons. So 1, 2, 3, 4. 1, 2, 3, 4. All right, and so 6 minus half of 4, which is 2, minus 4 is equal to 0. So the charge on this first atom is 0. 0 charge. Let's try to do that with this middle atom. So it's given 6 from the periodic table. It's got 3 bonds, and so therefore 6 electrons. So half of 6 is equal to 3. And so I have 6 minus 3 minus 2 pairs of electrons. Oh, sorry, well, 1 pair of electrons, so 2 electrons that are non-bonding. And that's equal to plus 1. So the charge on this atom is plus 1. Finally, for the last one, I have 6 electrons from the periodic table. Half of the bonding electrons, there's only 2 bonding electrons, and so that's 1, so 6 minus 1. And then I have 6 of these lone pairs, or 6 of these lone electrons, non-bonding electrons, and therefore I'm equal to minus 1. That means this atom is equal to minus 1. And in order to find the whole charge of the molecule, Then what you need to do is just add up the charges. 0 plus 1 minus 1 is equal to 0. So the total charge of this O3 molecule is 0. If I added them up and I got a different number, then that number is going to be what represents the charge of the entire molecule together. So you can find the charges of each atom individually, and then once you have every atom's individual charge, you can find the full charge of the whole molecule together. And that concludes chapter 7. So if you have any questions, please let me know, and I'll see you guys in class. Take care.